Okay, today we're talking about the invisible armor that protects pretty much everything we touch. I mean, from the chip in your computer to the glasses on your face, our entire world runs on these high-tech coatings. But what if I told you that creating this invisible shield is actually one of the toughest challenges in modern science?
Seriously, think about it for a second. That little piece of glass in your pocket survives keys, coins, and, let's be honest, countless drops. What's the secret sauce that gives it that almost superhuman durability?
Well, here it is. The secret is a coating that is 1,000 times thinner than a single human hair. It's applied using this process called vapor deposition, and the technology is so mind-bogglingly precise, it's almost hard to believe. And yet, it's literally at our fingertips every single day.
But here's the catch. Making that flawless, seemingly magical layer is a minefield of technical problems. Let's peel back the curtain and look at the hurdles scientists have to overcome just to get this stuff to work. It really boils down to 4 big headaches. You've got physical failures, like the film literally tearing itself apart or just not sticking. Then there are problems with control and making sure the coating is even. Of course, there's the huge cost in both money and energy. And finally, you've got some pretty serious environmental and safety risks.
All right, let's dive into that first set of hurdles. We're going to look at what can go disastrously wrong at the microscopic level when you're trying to lay down these ultra-thin films.
You know, inside every single one of these coatings, there's this hidden battle going on against something called residual stress. Just imagine a tightly wound spring. This happens when the coating and the surface expand at different rates or when temperatures change too fast. All this stored up energy is just sitting there, waiting for a reason to snap. And when that spring finally does snap, this is what you get. The coating literally rips itself apart. It cracks, it peels away from the surface, and just like that, the entire component is totally useless. But stress isn't the only enemy here. I mean, what if the coating doesn't even stick in the first place? That's the most fundamental challenge of all: adhesion. For engineers, this is a constant battle. On one side, you've got the adhesion killers, like a surface that isn't perfectly clean. But on the other, you have these really powerful solutions. Think of plasma activation. It's like using an energized gas to hyper-clean the surface at a molecular level. Or you can use special primers that act like a microscopic, super strong double-sided tape, making sure you get a perfect bond. Now, getting a perfectly uniform coat, that's another huge problem, especially with a method called physical vapor deposition. The easiest way to think about it is, it's just like a can of spray paint. The coating material travels in a perfectly straight line, so any part of a complex, 3D object that's tucked away in a shadow gets completely missed. No coating at all. So you can see that achieving this kind of microscopic precision isn't just tricky from a technical standpoint, it also comes with a really hefty price tag, both in cost and in energy, and that creates some serious limitations. Just look at that number. A lot of the highest quality coating processes out there need temperatures between 500 and 1,000 degrees Celsius. That is incredibly hot. I mean, we're talking hotter than your oven on its highest setting, and in some cases, it's hot enough to melt aluminum. And that extreme heat creates this really hard barrier. Sure, you can coat tough stuff like metals and ceramics, no problem. But what about everyday plastics, lightweight composites, or delicate electronics? Forget about it. They would just melt into a puddle. And then there's this constant tug-of-war between how something looks and how it actually performs. You might want a beautiful, sleek, mirror-like finish on a product, right? But that very same reflectivity could actually hurt its optical performance. Or maybe you want a vibrant color. But to get it, you might have to sacrifice how durable the coating is. It's always a balancing act.
Now, these challenges aren't just stuck inside a lab. The processes we use to make these amazing coatings have some pretty significant real-world consequences for our environment and for safety.
The whole process relies on some seriously hazardous materials. We're talking about toxic gases like silane, corrosive byproducts that have to be dealt with, and tons of chemical waste. All of this stuff poses a direct risk to the people working with it and to the environment. This chart really tells the story. First, look at that bar for energy consumption. It's just massive. That's from having to maintain vacuums and those extreme temperatures we talked about. And of course, that leads directly to a huge carbon footprint. Then you see that last bar? Once you put one of these coatings on a component, recycling it becomes incredibly difficult, if not impossible.
But you know, it's not all doom and gloom. For every single one of these challenges, brilliant engineers and scientists are developing some really cool solutions. So let's look at the path forward.
Hey, remember that massive heat barrier? Well, this is how we get around it. By using an energized gas, a plasma, we can create those same amazing high-quality coatings but at much, much lower temperatures. This is a total game changer because it finally makes it possible to coat plastics, polymers, and all sorts of other sensitive materials.
And to tackle all those safety issues, the field is moving towards what are called green precursors. Basically, scientists are designing brand new, non-toxic molecules to build the coatings from the ground up. It takes the hazardous chemicals out of the equation entirely. Pretty cool, right? So how do you make sure that every single one of the millions of phone screens rolling off the assembly line gets a perfect coat? Simple. You build a digital twin. It's a perfect virtual copy of the entire process that uses AI and a ton of sensors to catch any errors before they even happen. This is what guarantees a flawless coating every single time on an industrial scale.
You know, this quote really sums the whole thing up. Progress in this field is this constant balancing act between making coatings that work better, are cheaper to produce, and are safer for the planet. You can't just push on one of those. You have to advance on all three fronts at once.
So as we keep solving these challenges, making coatings that are smarter, greener, and more capable than ever before, the real question isn't just about what we can protect. It's about what new worlds we can build. Self-healing materials, flexible electronics woven right into our clothes. The next generation of so-called impossible materials is just waiting to be discovered right beneath the surface.